Welcome to part 6 of the Dueling AI Self-Play Reinforcement Learning series. So today we're going to go ahead and dive in to our buffer class in order to store past experiences for the agent to learn from. So let's go ahead and add a buffer.py. And in buffer.py, we're going to need a few imports. So we'll go ahead and import torch. We will import numpy as np, and we will import os. We're going to need all of those. Let's go ahead and call it replay buffer. And in our init method, we will need a few params here. So we're going to do max size, input shape, n actions, input device, output device, which we will default to CPU, and frame stack, which we will default to 3. And let's talk about the input device and output device. So one of the things that you can run into is the performance differences between things stored on your CPU and things stored on your GPU. And when I say stored on your CPU in this context, it just means that things that are in regular system memory. So when you're running something with a replay buffer on CPU, on system RAM, and you are training with on your GPU, of course, then you're going to be basically sending batches back and forth to your GPU constantly, thousands of times a second. And what that ends up looking like from a resource utilization perspective is you'll see your CPU sitting at 400, 500% with multiple cores effectively just sitting there pushing data back and forth, which can be okay. If you're trying to run this on a GPU that doesn't have a ton of memory, then that's the best way to do it, is to store things on CPU and on your system RAM, and then send those things to the GPU as they're needed. If you have the memory on your GPU to handle storing your entire replay buffer, however large that is, on your GPU, then the best thing to do is just push everything to the GPU, and don't store anything on your CPU, on your system RAM. And then when you send a batch to the GPU for training, it's just already sitting there in memory. And you're going to see your CPU usage go down to 100%. It'll just be one core running whatever the environment is at full speed, and then all of that load goes over to the GPU, which is a lot more efficient, and it's going to run faster. So what we're going to do is we're going to build out this replay buffer class in a way that lets you push data to the CPU or the GPU depending on your system requirements. So let's go ahead. And honestly, even if you normally work on the GPU, it can be convenient to have system memory as an option. If you want to test something, crazy, like, hey, what happens if I give this thing a million lines of replay buffer across 48 gigs of RAM, does it improve performance? And maybe it'll run a little slower while you're testing that, but you can test it, whereas you might not be able to if you're forcing everything onto the GPU statically. Okay, let's go ahead and start coding. So we're going to do self.memSize is equal to max size. We'll do self.memCTR, and that is your memory counter, is equal to 0. And then we're going to go and grab an override variable. So I'm going to say override equals os.get env replay buffer memory. Okay. So what I wanted to be able to do is hard code this in one direction in the code base, and then set an environment variable if I'm running it on a system where maybe I want to cut over to CPU or a secondary GPU or whatever we're doing. So we're going to say if override in CPU, CUDA 0, which is the first GPU slot, or CUDA 1, then print received replay buffer memory override to, let's go ahead and make that an, and then we can do override. And then self.input device equals override. Okay. Else, we just set self.input device equal to input device. Okay. Self.output device will always be output device. That's basically always going to be GPU. And then we want to go ahead and start our memory. So this is going to be the standard state memory, next state, action, reward, and terminal or done. So we will say self.state memory is equal to torch.zeros. And in a second set of parentheses, we'll do max size and star input shape. And then here we're going to do dtype is torch.uint8 device is equal to self.input device. For self.nextState memory, we're just going to copy and paste. And let's see why we don't like, because for some reason I typed torch.device or it auto-corrected to torch.device, and that was not necessary. That is not something you can put there. All right, so state memory and next state memory are going to be the same, which makes sense. Action memory, so self.action memory is going to be equal to torch.zeros, and we'll do max size. Dtype equals torch.int64. And then device is equal to self.input device. All right. Reward memory will be very, very similar. So that's going to be, this is one that we are going to do float 32. And input device equals input device. And then self.terminal memory. So the dones, in other words, in this case, it's going to be torch.bool. And again, device is self.input device. So again, our input device is where things are actually getting stored. Okay. We're going to define a can sample method. So def can underscore sample, self, batch size. It takes an int that helps with some of our tips later. Bool. And we're just going to return self.memctr greater than or equal to batch size times 10. So what we're doing with memcounter, there's a couple different ways you could do this. You could have a dynamically expanding memory, and then you could, just slowly expand that up to the max size and then cut off entries that are higher than that. I prefer to go ahead and allocate everything right up front, because that's going to tell you in the first 30 seconds of the program running if you have a memory issue, a buffer that's too large, something that's not going to fit on your system or your device. So what we're doing is we're effectively setting the amount of memory that's full to the mem counter. So when we get to the storage section, we're going to define, which we're going to do in just a second, we are going to define an index. And that index will basically step along the buffer until the buffer is full. And then it starts at the beginning and starts overriding. So there will be one space in memory declared that we will then fill up with our data instead of slowly building that up. So let's go ahead and do def store transition and self state action reward next state done, and idx equals self dot memctr. We'll do modulo self dot memsize. So this is the starting. This is what's going to make it effectively start at the beginning. As mem counter continues, your index is going to get to the end and then loop back to the beginning. Self dot state memory idx equals torch dot as tensor, and we're going to do state dtype equals torch dot uint 8, basically the same thing we did earlier. Device equals self dot input device, and then we'll do the same thing with next state memory, except over here we're going to call next state and put that in next state memory. And then here we'll do self dot action memory index is equal to int action. Oh, that's not what I wanted. And then we'll do something similar with reward and terminal. And then over here, instead of int, we'll do float. And that's just in case you want, a non-integer reward. We're not actually going to use one here. Done. Okay. That looks good. And then finally, we are going to say self.memCounter plus equals 1. Okay, so that's our store transition. So this is what's going to get called over and over again to fill the buffer up. Okay, then we can do our final method for this one, and that is def sample buffer. And that's going to take self and batch size. And here we're going to say max mem is the minimum of self.memCounter, because again, that's going to be the point in the buffer where we're at, and self.memSize. So if memCounter is smaller than memSize, we're going to grab things that are up to memCounter. That's the part that's full. If memCounter has made it over memSize, then we're just going to grab something that's in our available memory. So our batch is going to be composed of torch.randint 0 to maxmem of batch size and device is going to be self.input device, and dtype is going to be torch.int64. Okay, so this is going to grab a batch that's a bunch of random numbers somewhere between 0 and whatever this came back with. That's basically what we're doing here. And then we can use that batch of indices in order to pull back our states, next states, etc. So we're going to grab states is equal to self.stateMemory batch and .2 self.output device dtype equals torch.float32, And these are all going to be somewhat similar. So next states, and we're going to do next state memory. Just don't accidentally miss changing one of them, or you'll end up with states getting returned as next states or something like that. And that can be a really confusing thing to troubleshoot. All right, and then rewards is going to be self.reward memory. And in this case, dtype is going to be output device. Or not dtype equals output device. I'm misreading that. For these, we actually don't need to set the data type. We should be good. All right, and then we'll just remove the too much. We'll go ahead and do dones is equal to self done memory. Did I call it that? No, I called it terminal memory. Okay, so we're going to do self.terminal memory, batch to self.output device, and then we're going to have actions is equal to self.action memory, and we will grab our batch, and then we'll do self.output device. And then we're finally at a point where we can return states, actions, rewards, next states, and dones. And this is a good time to stop and read through this and just make sure that there are no typos, nothing missing. So we've got batch, torch rand int, batch size device equals input. That all looks good. We've got states matching to state, next states, next state, rewards, done, terminal, action, and actions. All right. That all looks pretty good. That looks like it's in a good place. All right. So let's go back to our agent. All right, and inside of our agent, we are going to come down here above the model and under our observation. And we're just going to go ahead and declare self.memory is equal, and really our model here should be self.model. So self.memory is going to be replay buffer. Max size is equal to max buffer size. And actually, let me see. Yes, I did import replay buffer. Cool. Thought I did. Input shape is going to be equal to oms.shape. And actions is going to be equal to self.env.actionspace.n. This is where we get to be a little bit more dynamic because we built this out as a somewhat proper environment. Input device is equal to self.device, and output device is equal also to self.device. So for now, we're just going to run everything on GPU. Okay, it seems like it worked. It seems like we successfully loaded up. Let's just do a quick test to see if it actually loaded on the GPU. So I'm going to import, and I'm sure there are much cleaner ways to do this. But instead of ending immediately, we're going to do time.sleep 30. So we're going to set a 30-second sleep. And our max buffer size is, what did we set that to? Our default is 100,000. So what this should look like is this should look like something over here. If I look at NVI top, and what you can see is that 100,000 is taking up 40 something percent of the GPU. And this is a 3090, so that's 10 gigs or so. If we kill it, then what we should see over here is we should see things. Oh, hang on. I was looking at utilization, not memory. Let's go ahead and rerun that and see what shows up under memory. Okay, 27%. So 27%, about a quarter of our 24 gigs. So that's where we are with 100,000. The actual amount that we're going to end up training with later is 200,000. So let's go ahead and set that and see where that lands us. All right. So the 200,000 lands us at, 10-ish gigs of GPU memory used. So that's okay. That's what we were expecting. If you are running something that does not have that much memory, if it's only got, say, 8 gigs, you do want 200,000 max buffer size. You can try it with smaller. So let's go ahead and see if we change input device from self.input device. We're going to try this a couple different ways. So we're going to do self input device CPU. And what we should see now is GPU memory is nice and low. But if I sort CPU memory, I get 8.4 gigs used by Python, which is what we would expect, right? We're storing our entire buffer on system memory. Let's go back to self.device. Again, just doing some testing here. So at this point, we no longer see 8 gigs used. We are, in fact, our Python isn't even showing up in the top of our resource utilization here. And then to do a final test, let me go and let's, for me, this is a build.sh. You can obviously do it by hand. But let's go and test our override variable here. Oh, that's not what I wanted. So replay buffer memory equals CPU. Let's try that. And what we should get is creating agent with device. I don't yet see our, let's see. I left off a set there. Okay, we should be getting a printout from our script telling us that we have that we've built something out with an override. Okay, I think I need to actually do an export. Hey, there we go. Received replay buffer memory override to CPU. That's exactly what we expected. And what we should see now is we should see that we are back on the CPU. We now have 8.4 gigs of memory, not on our GPU. So we have a successful replay buffer. We are pushing it to the appropriate memory. We're able to create it with either scenario. I actually don't want it going to the CPU, so I'm going to save that off. And we will go ahead and delete this time.sleep. And that is probably a good place to go ahead and break this video. In the next one, we're going to go ahead and dive in to filling the rest of this agent class out, and we might even get as far as a training loop. So with that, I will see you in the next video.